This is the MES 321 group project on the use and structure of zirconium hydride. My name is Jadin Swarts.
I'm Tyler Bloom.
And I'm Jackson Keppen.
Reactor control is the most important aspect of reactor physics and design. Control rod manipulations by operator control in a reactor are used to change neutron populations, maintain flux shapes and magnitudes for radiation purposes, and practice safe operating procedures. In any reactor, the integrity of the fuel cladding protects against the release of fission products, and the temperature of the fuel must be maintained under strict values in order to ensure the safety of the reactor. All reactors have the ability to carry out what's known as a pulse once, but only certain reactors can pulse repeatedly while maintaining reactor integrity. A pulse is an insertion of more than $1 of reactivity, which results in the reactor becoming prompt supercritical, a state where the neutron population is increasing exponentially on fission neutrons alone. When prompt supercriticality occurs in a bomb, an explosion occurs. When it occurs in a trigger reactor, the characteristic pulse occurs. Depending on the size of the reactor in operation, energy levels during a pulse can reach upwards of 22,000 megawatts as compared to an average 1 megawatt steady-state operational limit. Because reactor pulses occur on the order of microseconds, reactor operators cannot respond quickly enough to control the pulsing process. This requires other means to be employed in order to control the nuclear chain reaction, such as the use of different fuel compositions and structures. The Oregon State Trigger Reactor utilizes a zirconium hydride alloy in its fuel in order to induce a strong self-regulating characteristic to the reactor during a pulse. This characteristic is the negative prompt temperature coefficient, which means that as temperature increases in the fuel, power and therefore neutron population is decreased in response. It is the zirconium hydride lattice structure that causes the negative temperature to be so large in the trigger reactor due to its unique neutronic properties. Zircaloy is the primary reason pulses in the OSTR can be conducted safely, and the trigger reactor should never reach fuel temperatures that would result in damage to the fuel cladding due to its use.
Zirconium hydride has 4 main lattice structures with different abilities to absorb considerable amounts of hydrogen. The alpha form is hexagonal close-packed and is the most stable form of zirconium, absorbing at the most 0.069 weight% hydrogen at 823 Kelvin. The beta form is body-centered cubic and forms at higher temperatures where it's stable. It has the ability to dissolve a lot more hydrogen and still retain metallic properties, reaching close to 60% atomic percentage hydrogen. The delta form is known as fluorite and is face-centered cubic. This form occurs at higher concentrations of hydrogen, which is above 60% atomic percentage hydrogen. It is face-centered cubic, and as the percentage of hydrogen increases, it begins to distort and stretches the cubic into a tetragonal along one face. This deformation turns it into a weaker epsilon form, a face-centered tetragonal. The hydrogen is important because it creates multiple possible energy states that are able to closely mimic the energy levels of the thermal neutrons and act in a manner similar to a harmonica oscillator. This allows the hydrogen to exchange energy with incoming neutrons in order to create a high likelihood for a fission event within the fuel. The scattering occurs more readily as the temperature increases, increasing the overall energy of the system and decreasing the thermal neutron population. However, as the temperature increases, there is a possibility of the hydrogen dissociating, which is an explosive problem. The metallic properties of the zirconium allows for high thermal conductivity, allowing the fuel to release heat into the coolant effectively. It becomes stronger and more brittle as the hydrogen is dissolved within the fuel.
To create trigger fuel, non-hydrated zirconium is melted down and combined with 20 weight% enriched uranium and a small amount of erbium. The fuel mix in the end is about 69 weight% zirconium, 30 weight% uranium, and about 1 weight% erbium. This fuel mixture is then rolled out into tubes that are about 15 inches long and 1.5 inches in diameter. A small hole is bored axially through the tube to allow the hydrogen to diffuse evenly throughout the zirconium. The annealing process is done in a hydrogen-rich atmosphere with temperatures somewhere between 400 and 600 degrees Celsius in order to form the delta phase of the zirconium hydride, and this is maintained long enough to form the 1.621 hydrogen to zirconium ratio. A small tube of pure zirconium is inserted into the bore to maintain a void-free macrostructure for the fuel. The final step for the fuel is to be wrapped in a thin cladding of steel in order to reduce hydrogen diffusion out of the fuel meat. A steel clad that is 1/4 of a millimeter thick will keep the escaping diffusion rate below 1% of the hydrogen content per year while the fuel is kept at 500 degrees Celsius. However, we know from the diffusion equations the rate of diffusion goes up exponentially with temperature. The hydrogen can diffuse out just as easily as it diffused in. The Fukushima Daiichi nuclear disaster occurred because the fuel could not be kept cool enough and the hydrogen diffused out of the fuel and then reacted with oxygen in the high temperature environment. This caused the explosion that is the reason for the radioactive release. And on that happy note, thank you for listening to this presentation of trigger fuel and zirconium hydride. Here are references.